We'll solve this today's LeetCode problem. This is LeetCode medium. Balance a binary search tree. It's a LeetCode. It's again a binary search tree question, right? Let's see the question. So here we have given the root of a binary search tree. We need to return a balanced binary search tree with the same node values. If there is more than one answer, return any of them. So basically, what is a balanced binary search tree? So we have already given our definitions that a binary search tree is balanced if the depth of two subtrees of every node never differs more than one, right? It means, what does it mean? That any node, from any node, if the binary search tree balance, it means from that depth of two subtrees of each and every node never differs by more than one. If you see in this example, this three part, if you see the cursor here, this three part, if you see its subtree's depth, it left side, its depth is 2, because it has, it can go to two depth, right? 1 and 2. And its right side, it has a depth of 1, so 2 minus 1 is 1. It is not more than 1, it is less than equals to 1, right? So that's the meaning of depth of two subtrees of every node never differs by more than one. If you see in this example, the second image, this two part, if you see you can see the cursor. This two subtree is 3 and 4, which is 2, and this left subtree is 1, which is 1. 2 minus 1 is, so absolute. It is the meaning of that absolute difference, absolute height of the subtrees, or depth of the subtrees should be absolute difference of right and left must be less than equals to 1, right? So balance means that absolute difference between left height, left depth subtree, left depth, left subtree depth, right? Left subtree depth minus right subtree depth must be less than equals to, one, right? This would be for each and every node, right? This will be true for, this must be true for each and every node present in of BST, right? Of BST, right? This should must be true for each and every node for BST, right? So if you can see for this three, so this three, right subtree is 4 and left subtree is null. It means 1 minus 0, which is again 1, less than equals to 1. So that's the meaning of balance. Okay, so basically we have given BST. If you can see first example, 1 2 3 4, it's a valid BST, right? But it is not a balanced. Why? Because if you see the one, it has right subtree depth is 3, but in left it don't have any, it doesn't have any uh, children or subtrees, right? So 3 minus 0 is 3, which is greater than 1, right? So we don't, it is not a balance, so we need to convert this into a balanced subtree and return the root of that balanced binary search tree, right? Balanced BST, right? So for that, there can be possibility, many possibilities to make that, but we need to return only one of them, right? If there is more than one answer, return any of them, right? So we need to return any of them, right? So basically, so here if you see, if I want to return, if I take start with three node, this three node, so if I start with three node, how will I make BST? So if I start with three node, the first thing is that, okay, you, we already know the definition of BST, that the left node would be less than the current node, the root node value, of course, right? Root node value, left node value must be less than root node value, and right node value must be greater than left node value, sorry, root node value, right? That's the definition for each and every node present in BST. That's the needs to be required. This is the condition of BST for each and every node, for each and every node, for each and every node, right? Node of BST, right? This is the condition you need to fulfill, we need to fulfill, right? Okay, we understood the BST condition, we understood the balanced BST condition, right? Now, to start from 3, to make the root of the 3 as a node, right? To make the 3 node as a root, right? To make the 3 node as a root, what, how we will make? So we have we have 1 2 3 and 4, right? This is the nodes we have, right? So if I start make the root node as a 3, so this 3, what would be the left and the right, you tell me? what would be the would be at left and the right. So if I want to put the left, what numbers can I put? I can put 1 or 2, right? So suppose I can I put 1, right? Now when I want to put 2, where I will put, I will move to its left part because 3 is greater than this 2, right? But 2 is greater than this 1, so it will be put at the right of 2, right? That's why I can put it at the right of 2, right? That's the meaning of this. Okay. Also, if you see here in this case, this 3, this 3, 4 is greater than this 3, it means it will be put at 4 parts, right? So this is how BST will form. This is how this BST will form, and this BST is valid, right? Of course, this BST is valid because each and every node is satisfying these two conditions. But whether it is a balanced or not, we will check that, right? So if you see, for this 3, its left subtree height is 2 and right subtree height is 1. It means 2 minus 1 is 1, which is less than equals to 1, satisfied. For this one again, right subtree is 2, which is 1. Right subtree is the height is 2, is which is 1, and left subtree height is 0, which is 1 minus 0 is 1. So again satisfied, right? So if you see at 4, it is already satisfied. No values, no children at left and right subtree both. So 0 minus 0 is still 0, which is less than equals to 1. So it is also a balanced. It is also a balanced BST, right? So it means it can be our answer. It can be our answer, right? So one thing is also here that here we see that we need to we need to make the BST only with the same node of values. It means I need to use these nodes only. I need to use only these nodes for sure. For sure, I need to use only these nodes, right? So basically, if we see again that if I need to use these nodes only, so there can be other possibilities which you have seen here. There's 2, 1, 3, 4, right? This can be also possibilities. If I started from 2, I have started from 3. That's why this BST form. If I started from 4, let's suppose I will try to form for 4, right? So we have 3 nodes, 3 to 1. These all nodes are less than this 4. So where will this go? This will goes to the left part. This 3 will go to left. This 2 will go to left. This will go to left, right? This one will go to left, right? So if you see this 4, 3, 2, 1, or you if you try to put the 2 first, so this 3 will go to at the left of the right of 2, right? This one will go to at uh, the left of the left of uh, the left of 1, left of 2, right? If you try to put 3 first, right? So in any of the case, either you put 2 or 3 first. See, here it is 2 here, and in the left part, right part, there is no children. So 2 minus 0 is 2, which is not a balanced BST, right? Which is again not a balanced BST. This is not a balanced BST. So if you observe here, for making a balanced BST, if you for making a balanced BST, for making a balanced BST, making a balanced BST, I need to uh, I need to put equal number. I need to put the nodes in left and the right subtrees for sure, for sure. But I need to also maintain. I need to make it balanced. So basically, I need to put equal number of trees. I will try to. I will try to. I will. I need to. I will try to put the same number of nodes in the left and right, so that it will always not exactly same number of nodes, but only the difference between only the difference between, not the only the not exactly the same number of nodes, but I will put the number of nodes in left and subtree, right subtree, such that the difference would be will not be greater than 1, will not be greater than 1 for each and every node. That's how I will put it. So for that, how do you think that I will do? Can I take a maximum can I take the maximum value, right? Can I take the maximum value like 4, or can I take the minimum value like 2 1? No, I can't take this. But then how so I need to take a middle values which can form a root. So the first thing is that I can make the root. I can make the root. I can only make the roots. I can only make the roots. Make the roots which is not maximum or not minimum, right? So what would be the ideal condition for making a root node? So if you see, so if you see in this tree, if the tree's value, if the tree value gets sorted in order of, if the tree nodes get sorted in order of their values. In first case, let's suppose there are given five nodes. So 1 2 3 and 4 5, right? These are the nodes in the in any of the tree, any of the bsts. These are the nodes which is in the sorted order, right? And if I want to make the balanced bst from these nodes only, so basically I have just sorted the values of bst, right? So if I want to make this balanced bst from these nodes, so what would be the ideal conditions to make to so which element I will make, I will take for the root node. For the root node, what is the ideal element? Of course, the mid element. Don't you think that three? If I made a three element as a mid element, this one and two will go its left part. 4 and 5 will go at right part. If I make a mid element as a root node, then I have the uh, the same number of nodes in left and the right subtree. Highly chance, it's a high chance, right? It's a high chance to that I have equal number of nodes in right and the left subtree. But what if it is not even number? Let's suppose there is 6. So if I also take a middle element like 3 or 4, any of these elements, so either three elements will go at left part and two elements go at right part, right? So again it's left part minus right part is again less than equals to 1, right? So it means mid element would be the ideal condition that I will make as at a root node. In even an odd number of nodes both, right? Okay. So I have understood that the root node would be must a mid element, right? So the the second thing, okay, I understand the mid element would be must be root node. Also, that how will I make the BSTs? So if you see, if I take these nodes and if I have take a mid element, either it can be 3 or 4. It is a 6 elements so total would be 3, right? So you can take either 3 or 4. So I take 3, right? You can take also 4 as a root node, right? It's totally upon you. So if I take a 3 node, so for 3 node, what would be the possibilities to put the left and the right part, right? What are the possibilities? So if I want to put in the left part which is 1, so that would be only this 2, right? This would 2 would be at left part, right? Because this is less than this 3. And also when I want to one where I would put, I can put this at right left for this 1, right? And if I want to put 4, where would I put? I can put this at right of the subtree which is at 4. So that would be 4. Again I want to put a 5, so that would be at again 5, that is this 5, right? Again I want to put 6, this will go to this part. So either you can form like this, or you can form anything you want, right? Anything you want, this will make definitely a bistate. See, 3 minus 2 is 1. 3 in the left part, 2 is right part, 1. 4 for 4, this is 2. This will never be, this will never be a balanced binary tree. Why? Because 4 right subtree is 2. This is not a balanced binary tree. This is not a balanced BST. Why it goes wrong? Because you have taken a mid element as a root node. But you have taken only the root node as a mid element, not for the its left part and the right part, right? It means, what does it mean? We need to always take the mid element for each and every step, at each and every step, at each and every step. Why it is so? Because for maintaining the balanced binary search tree, for each and every node the depth of two subtrees must be less than equals to 1, right? So for each and every node I need to take the mid elements for at each every step. That's why can uh, can equally distribute, right? So that's how this 4 will not this 4 is not a mid element after taking this 3. So that's why this is not a balance tree and not equalized. So for that, how we will do? So if you take the 3 as a mid node, which is a balance, which is a mid value according to this 1 2 3 4 5 6. So 0 1 2 3 4 5, right? So if we, this is the balance 3, so it means after this right position, after this right positions, from 3 to 5, from 3 to 5, you need to check which is the mid element now, because you need to take a mid element for each and every step. And for the right positions, what are the possibilities for here, for you? All the elements which is greater than this 3, which is 4 5 6 only, so that would be 3 4 5. And what are the mid element? 4, which will be 5. So you need to put 5 at the first, at the right position, right? And what would that left part? That would be that would be, so you need to check for in the left part of this, right? You need to check for the left part of this, which is 2 and 1 only. And what the mid element? So anything between either 1 or 2, anything will work, right? So either you can write 1 or you can write 2, right? So for that I will write 1, right? I will take for 1, you can take 2 also. Now again for 1, after this 1, you have taken already this one, so you have only left with one value, which is 2. So that would be at right position. So let's put that in right position. So that would be 2. Now this for 5, you have already taken 5, you have already taken 5. What are the possibilities now? So for this 5, there can be a form a left tree and right tree, right? So for 5, what is the left tree? Because we have already used this, you don't need to see this now, you are already used, you already need to see this only. And now you have gone to 5, you are left with only 4 in the left part and the right part is 6. So 4 is, would be there at, 4 would be at here in the left part, and the 6 would be at right part, which is at 6. So if you see now, this is a balanced tree. How? See, for 3, 2 minus 2, which is 0. For 5, 1 minus 1 is 0. For 1, 1 minus 0 is 1. So 1 4 6 0 0, 2 4 6 is 0 0. So it is a balanced binary tree. It is a balanced binary tree. Balanced BST. What is the, what I'm trying to tell you by showing, by showing all you this, like, so see, we need to just first take all the values which we have, right? Take we need to know all the values which we have in our given BST, right? And I need to create a balanced BST from these values, from these values. That's the meaning of this, all the things, right? That's the meaning of all this. And how we will do that? So basically I just need to sort them, sort the values to know the mid element. So for sorting, I need to sort the values. I need to sort the values to make a balanced tree, and because we need to take a mid element for that. And for sorting, for sorting, if you know, there's a concept of in-order traversal, right? In-order traversal. I've already told you yesterday, reverse in-order traversal. I also discussed what is in-order traversal. That's a left root right traversal, right? we will move to left, then root, then right. So in order traversal gives you in order traversal in order traversal gives you the sorted order, gives you the values in sorted order, always it gives you for bsts, of course for bsts only, not binary trees, for bsts only, for bst only, right, not in binary tree, for bst only, gives you the values in sorted order, always for bst, right, for bst only. So if I will move in order traversal for this bst and store all the values in a different array, right? And what will I do with this array? I will use this array like this: 1 2 3 4 5 6. That I will take a mid element, then I will form a root node, then I will move to left part. Again, I will uh, do for the same thing, that again I will make a root node for the in the left part and also in the right part, and do the same thing again and again, again, right? That's why how we will form this balanced binary tree, right? So so suppose I have got this example 1 2 3 4, right? So this is the same thing which we I am doing this here, right? I will take mid element as a root node, and put and and attached left values of the array to left subtree of node, and the right values of the array to right subtree of node, right? And same thing goes on and on for each and every node, that I will make that element as a, I will take the see mid element is 3. So I will, for left subtree, 1 and 2 values are possible, but which value should we take? So we need to take the mid value, uh, which is between in this left part only, in the left of values. So mid values is 1 and 2, is 1 and 1, or either 1 or and 2. So you can take any of thing, and the same thing goes in the right part. So in the right subtree, which value should we take? We need to take the mid value between 4 5 6, which is 5 value, because it's the three numbers. So you will take 5. Again for 5, make this 5 as a separate, forget about this 1 and 2 3 values, make this 4 5 6 as a separate bsts, right? Separate bst. So 5 is a root node. Again same thing you will see in the left part, 5 left, that which values are possible, 4 values only, because these values are already been used. So you have only this 4, so you will put this 4 in the 5. Again for 6 the same thing happen, right? So that's how you will make, again goes on and on. It it just like merge sort type. It just like merge sort, that you will split the elements, right? Split the left and the right, right? It's like, just like a merge sort, right? So you will see the code and you will understand how we are doing. But for shorting, just the concept is that we need to use the values to given in our bst, and recreate the balance from these values, balance bst for this from these values. And uh, creating that, I need to short it for finding the mid element, and for sorting we need to in order traverse, because this will gives you always in sorted order, right? And why it is giving you sorted order? Because it moves to its left part first, right? So left part then root. So in the left part you will first get the minimum element, then root, and you will store that root and goes to right. So that will gives you definitely the sorted order. So we will see that how it is working, right? So let's just try to implement it. I think I have make you understand enough. You can solve it right now if you want. So let's see how will this work. So first thing is that I need to, in order traverse, to store the values of bsts in sorted order. So I will take vector which will store the values in sorted order. And also I need to in order traverse. So I will move in order with roots and with this v. Okay, and this will be void because I'm not returning anything. I will just storing the values. So in order tree node root, and this would be passed at by reference, not passed it by values, because you already know I've already told you in many of the videos that it will not create, it will point to the same vector, not making an extra copy of that vector, right? That's why we will pass it by reference, right? So first thing is that we will need to move in left part, so I will move in left in order root left v. Then the root value, so the root value would be posed in this vector left, then root, then we will move in right part. And in order traversal is, it's very easy, right? the same the same thing we have iterated. So yes, that's the whole thing. Now when this recursion will end, it will end when this root is null. If this is root is null, we will just return, right? So this is just a in order traversal. Now we have got all the values in our vector in sorted order for sure, because this will give sorted order values, sorted values, right? Now I need to form a balance bst. For that, what I have told that we need to take a mid value. So we will start doing that. So how we will do that? So just make a balance bst, and this will give me root value. So what I will do, I will just return that, right? So this is a balance bst, is balance bst, right? So let's just pass it root, or because this root is not enough, I need to just use this vector for making that. So I will just pass v, and the 0 will the size of this v, and the last size will be v dot size minus 1, right? Or just pass it like that, and minus 1. It's totally upon you, right? It's totally upon you. And minus 1, right? Now I need to form the balance bst for that. So what I will do, I will make the balance bst. So the first thing that, how we will make the balance tree. So let's just pass fastly for that, vector end b and I. So this is the start, this is the I, the start point, and this is the end point. Okay, now I need to take a mid value, so I will take a mid value. It's just a, and I will take a mid value, and what would be the mid value? Start plus end by 2. That would be the end value, right? So if that would be the end value, so the first thing that I need to make this mid value as a root node. So for that, I will make this as a root node. This will be root, and I will make this as a new root node. So new keyword is used in the C++. Also in Java, I think we need to something, I don't remember exactly in what in Java and Python. So they will something that to create a new node by constructive. So will you will see that in your language. So we will use the new node in we will use new node in mid values, because if you see here in the struct tree node, we have given this tree node value that if I put this x value as here, it will already generate left and the right pointer, right? So this is already made here, right? So I will just pass the mid value, which is b mid, right? Because this is the just a position, and b mid is the value. So that's make the new root node. And what we need to do now, I need to make it's a left tree subtree and the right subtree. So what I will do, I will again call this balance bst, and attach. What I will do, I need to attach some root value to its left value and also its right. So which values should be at left, which values should be attached to its left? The values which is less than this mid value, right? Of course, right? So what values would be there? So that would be from 0, and end will change to mid minus 1, right? this value would change to mid minus 1. Of course, for sure, because all the values which is less than mid will be less than this current root node, and that would be only present, should be present in the left part, and for right part, that would be balance vst b mid plus 1 till end value, right? And value is n minus 1, right? So that's how we will solve this, that at the left part it would be or take it as a start value, sorry, this would be a start, because if I simply make this 0, it will uh, it will not be 0, it will should be start, right? Because see, in this 456, in this 456, for this 5, its left part is 4, so it will start from 3 only, not from 0, right? So that's why I need to initialize with the start, not 0. So start to mid minus 1 and mid plus 1 to end, and this will gives me root ka value. And how will this give me? So when will the return condition will happen? So the main thing is that when we return this, so we will return only after this will be return root from here. After assigning this root left and this root right, we will return this. But when will this loop will occur, will return it, right? Because this is a recursive function, so it need to stop anywhere. What is the base case? What would be the base case? So if you observe, what are the changes we are doing? We are changing the start and the end value, right? This end is changing and the start is changing, right? So basically, if at any point start is greater than end value, start is greater than end value, we will need to return from that. And what we will return? We will need to return null, right? Of course, we need to return null, right? From there, if start is greater than end, right? We need to return null from there, because that would be, by returning null, because that would be the leaf node, this root would be the leaf node, that's why the condition is here, right? So this is how we will form this, and let's try to just run this, because this will be a perfect balance binary tree. Some compilation error occurs. V dot pushback. Okay, this would be pushback. uh Runtime root left. If root value is null, we will, okay, here also compilation error. Yeah, we have passed the cases. So basically, it's in order traversal is used for sorted order, to store all the values in sorted order, and this balance BST is using for, it's just like forming a BST from sorted BST. Right? It's again a different question. You will got, you can solve a question that sorted, uh, make a BST, make a BST from sorted array. That's the popular question, and you must have solved that. It's the same problem. It's a part of that problem. Make a BST from sorted order, right? You can solve this if you want it. I will give you the link in the description. You can solve this. Make a BST from sorted order. The same concept from this, right? So hope you liked it and understood. Okay, time complexity, right? Time complexity would be, so this time complexity would be that first thing is that I need to make in-arrow traversal for storing the VST. And okay, one thing you have come in your mind, that why haven't I used in order, why haven't I used any other things and just put all the values in V and sort it? So if you see here, in order traversal takes you O of n only, right? Because we need to traverse only one time to each node. So that would take O of n only. But if you use any other traversal and put the values in V and sort it, that would take n log n, of course, right? That would take n log n, which is not effective. So optimal is in order to traverse it. So that's why I have used in order here. So that's the one thing here. Second, that would take O of n for in order. Again, I am using balance BST to balance it. So that will iterating in whole of this nodes to make a balance BST. So again, O of n, and you can, so you can also take stack time complexity, and for the space, for the space complexity, That would be again O of n. The first thing is auxiliary stack space, that would be occurs in order and this balance BST both. And the second thing is that we are also using, also creating a new BST, right? We're also creating a new BST, binary search tree, for after recreation and returning its root. So that's definitely gonna take O of n only, right? That definitely take O of n. And also for auxiliary stack space, that would be O of n. So ultimately it is O of n. So that's the time and the space complexity for this problem, right? So this is how we will solve this problem. Thank you so much. Bye bye. Hope you liked it, right?